Hello all. So as a continuation of my lecture series, we are going into the new topic of stability analysis, in which the first topic will be concept of stability. So we will have an input, and if this is the input, then if the condition is stable, so it is marked in the first column. So if it is marginally stable and unstable, the response is shown clearly in the picture. So why stability is important? So system stability causes blackouts and equipment failure. So equipment failure is a very serious issue. So it is just not just a word. So it is a serious issue like we have to take care in. So who will be affected if the equipment failure happens or it causes blackouts? So power grid operations, industrial plants and consumers. So these are all the people who gets affected if the system is not stable. And what is the impact if unsolved is catastrophic safety hazards and massive economic losses. Need for the solution. So traditional methods of ensuring system stability are often inadequate for complex model systems. So if we are going to deal with the lowest powers and a simpler characteristic equation, the traditional system solving methods may helpful. But when we go complex systems and higher order systems, then we have to go with first if we try also, we will have a trial and error and waste of time and failure. So there are many limitations of existing methods like inefficient trial and error tuning cannot predict the marginal stability and no insight into relative stability. So coming to the technological gaps and needs, mathematical prediction tools, quantitative stability measures, design-oriented analysis methods. What is stability? So stability, a system is said to be stable if every bounded input produces a bounded output. So we are giving some input and we are expecting some output. If the given input and the expected output are satisfied, then we tell that the system is stable. So if it is not satisfied, we tell that unstable. So if we get the partial output, then we tell marginally stable. So these are the three types of stable systems. Coming to stability analysis methods, we have root locus, Routh-Hurwitz and Nyquist criterion. So these three methods, whereas in Routh-Hurwitz, we can, it is very easy also, but it also have some disadvantages, but it can be solved for higher powers easily and very efficient formulas. Coming to root locus technique, it is a graphical representation of poles and zeros, and we go with asymptotes and centroid calculations. When we go with Nyquist criterion, then it is frequency domain method, which is used for open loop frequency response. So coming to Routh-Hurwitz stability criterion, let us consider a characteristic equation, and if there is no sign change, then we tell that is the stable system. Then if we have zeros in the first column, then we have to add an epsilon and we have to proceed with the problem. So coming to root locus, a graphical plot showing how closed loop poles move as a system parameter. Typically gain k varies from 0 to infinity. So coming to applications, determine the range of gain k for stability, predict transient response characteristics and design compensators to improve stability. Nyquist stability criterion, so methodology is a polar plot of open loop frequency response. So G of j omega and H of j omega, where omega varies from 0 to minus infinity to plus infinity. For stability criterion is for a stable system Z must be 0, therefore n is equal to minus p. So if for equation is n is equal to Z minus p, where n is the number of encirclements and Z is number of closed loop poles and P is number of open loop poles. So coming to the applications, power system stability, maintaining grid frequency and voltage stability under disturbances. And motor speed control, so precision control of speed in industrial drives despite load variations. And voltage regulators, ensuring stable output voltage in power supplies and generators. So here, when we go with the design thinking integration into the system, so as an empathize part, we are understanding the user needs and identifying the disturbances, recognizing safety concerns. Whereas in the define part, we are going to know how the system oscillates excessively, and the problem is overshoot and slow setting and goal is stable response. So our goal is to get the stable response. So ideate is we are going to use compensator designs and controllers in order to make the gain adjustments and make the system stable. So as a summarized part in the stability of control system, this is a very important concept which we go with Vibo stability and stability types, whereas stable, unstable and marginally stable. And this analysis is needed in order to have the limitations and gaps has been discussed. And stability analysis methods, we have three: Rauterwitz, root locus and Nyquist stability criterion. So using these three methods for the complex solutions even, we can find the stability of the system. And we have discussed about the applications. Thank you. Let's meet in the next video.